All right, so on this lovely day, we are going to be talking about space figures and cross sections. Our goal is to recognize polyhedrons and their parts. We're also going to visualize something called cross sections. So the first thing that we're doing, a solid. It's any three-dimensional shape. A three-dimensional shape. So it has length, it has width, and it has height. So first off, let's look at what foundational shapes look like. We've got two examples here of something called a polyhedron. Poly is the Greek word for many, and hedron means faces, Greek for face. So when we have many faces. Now look here at these two polyhedrons and look at these three non-polyhedrons. Go ahead and chat real quick with your neighbor. How do we identify a polyhedron versus a non-polyhedron? So the key thing here about polyhedrons is that every face is a polygon. That is, remember, polygons have no curves. Polygons have no crossing, and polygons also are closed. And these ones over here, because of the nature of the curves, here we've got what looks like a circle on the top and bottom. This, of course, is a ball, being a sphere, a cone. So it's the curves over here that make this non-polyhedral, if that's even a word. So let's look at some vocabulary. We already defined polyhedron. It is a three-dimensional object with all polygons as faces. But of course, we need to know what a face is, we need to know what an edge is, and we need to know what a vertex is. Now we're actually going to start backwards. Most of y'all, all y'all already know what a vertex is. Pretty much you can think of it as the corner, just like the vertex of an angle. Okay? So this right here is a vertex, as is this, and all ochito of these ones are. Those are 8 vertices. Notice the plural there. Okay, next, an edge. An edge is any segment that connects vertices. So it is the walkway that gets us there. So this guy here, and as we see, we've got 1 there, 2 there, 3, 4, 5, 6, 7, 8, 9, 10. So I counted them up as 10. Oh, but I still got 2 more, 11 and 12. So this one, in this case, the edges, I have 12. Down here, the vertices, I have 8 in this particular case. And of course, the last thing are the faces. And those are hardest to imagine. But the faces are the polygons. Learn to spell polygons. So if we counted this up, now as I draw, it gets it really sloppy. So you have to think organizational if you're not going to draw. So notice I have a top and a bottom. So that's 2. Then I have a left side and a right side. That's 4. And then I have the front and the back. So I'm completely sloppy and I completely lost the diagram, but I was able to count them all. So in terms of faces, we see that we have 6. So let's just take a moment to spend some time naming vertices, edges, and faces. Okay, so let's look at the vertices. The vertices are points. The vertices are points. So Z is a point, W, V, Y, and X. And in no particular order. So vertices are points. Next, the edges. The edges are segments. So, Notice there are quite a few of them, and keeping track of them in some way, I'm just going to do all the ones that are starting at Z and going down to begin with. So ZX, segment, ZW, ZV, and lastly from the top, ZY. Now that's not all of them, because I've only done the one that the 4 that shower down. Now I've got the 4 that are wrapping around the bottom there. So next up is YX, and I'm just going to go around like so, YX, XW, etc. Segment XW, segment WV, and segment VY. All right, and lastly we've got edges. Excuse me, we just did edges. Faces. Now it is face time. And faces are, in a polyhedron, they're always polygons. But we'll just say they're two-dimensional shapes, okay? So notice the logic that goes on here. Vertices are 0 dimension, because they're just points. Edges are 1 dimension. And faces are 2 dimension. All of these form together 3 dimensions. All right, so now my faces are as follows. I'm going to do the 4 that are going down from Z. So one of them is triangle ZXY, which is over here. Then another one is triangle ZXW in the back. Triangle ZWV on the right side. And finally in the front, triangle ZVY. And of course the thing that's on the bottom, it looks like it could be a square or a parallelogram. Since I'm not 100% sure what shape that is, I'm only going to write it with the letters. So XWVY is another face. Now I don't need to write all 4 letters for that. And in fact, up here I don't even need to write the triangles. It's nice to say triangles, but I don't have to, because in saying 3 letters, I'm saying that I have a polygon of sorts. So here I can say any of the 3 letters that are down below here, or all 4 of them. I did all 4 just because it's easy to point out there. Now, the key concept as we are looking at how the faces, vertices, and edges are related comes from a good friend named Euler. So please make sure that you pronounce this right, when you're talking about it, with your friends. Euler is how it's pronounced. So from the book, G is for Google, there is a story about a place called, and I'm going to spell this wrong, so let me look it up, Königsberg in Germany. And before this thing called the internet, and I like to sit all by myself in the middle of the night and look on the screen and not interact with anybody, people used to do this thing called walking. I don't know if you've heard of that, but you actually use your feet, and you usually walk with somebody, and you go around and see things. And sometimes you'll stop and talk to somebody, and sometimes you'll throw these things called rocks into water. And I don't know if you've known about this, but these things, sometimes you can skip rocks too, and they skip off the water. I know it seems to be like defying physics, but these are things that you discover when you go out into this thing called the world. And there are these trees, and there's lots of stuff to see instead of just YouTube and people falling off bridges. So, people used to do this crazy thing called walking, and there was this scenario where there was this island right here, and here we have rivers that kind of met, and here's an island.
Mesopotamia.
No, it was not Mesopotamia. Okay, but here's what people would do. Maybe their house was over here, and they would go across Wooden Bridge, and then go over High Bridge, and then go across this what's called Giblets Bridge, and then Blacksmith Bridge, and this other bridge, and they wanted to know if they could get all across the bridge and never cross one twice. But they also wanted to be able to see if they could get back to where they started. So they had this problem where they were just trying to do that. Oh, I skipped a bridge right there. So you try this one, all these different routes, and discovered, or at least nobody discovered, that they could. Nobody could get across all these bridges without having to cross one again. So it became known as the bridge problem. And they couldn't figure out why nobody could do this. Well, along comes a mathematician named Euler. And Euler discovered that there are certain relationships that are needed with, notice that each walking path could be an edge. And each vertex, so each one of these could be like the bridges here, and these can be the points where things intersect. And he came up with where we now are dealing with network theory. And it's all related. And one of the most simple concepts of it is that when you have a three-dimensional object here, that it has to be in this relationship, the number of faces you have, the number of vertices, and the number of edges. And it always looks like this. So faces plus vertices equals the edge plus 2. So just to give an example before, we had 6 faces and 8 vertices, and we had 12 edges. And notice that indeed we get 14 equals 14. So this is the one for the cube, or maybe a Kleenex box. Trademarked. So what we're going to do here is verify the actual number. So let's count them up real quick. 1, 2, 3, 4, 5. I have 6 vertices on top, 6 on the bottom, so that makes for 12. Next, if I'm looking at my edges, I have 6 on the top, 6 on the bottom, and 6 connecting in between. So edges, I have 18. And lastly, my faces, I have 1 on the bottom, so second on the top, and then 6 going all the way around. So it looks like my faces, I have 8. So above, it says faces plus vertices is equal to edges plus 2. So my faces are 8 plus the vertices 12 should equal 18 plus 2. And easily we see that it works out. 20 equals 20. So our friend Euler came up with a good hypothesis. It's been tested and proven. Because these two are actually the same shape in terms of name, not the same size. I'm not saying they're congruent or similar. I'm just saying they're both prisms with a hexagon as what's called the base.
Both hexagonal prisms.
Hexagonal prisms. So because of that, the same answer is above here. So there's no work. This is the exact same there. Okay. We're going to look next at cross sections, and by a printing error, the diagrams are on this page. So we're looking at these 3 here. So imagine you are making scones, and it requires you to cut up the butter in small, thin slices, and then you toss it into your flour before you have to mix it together. All right. We can slice this butter thing, in a bunch of different ways. If you wanted to, you could just take off a corner like this. And if I did, so notice I just put 3 little cuts there, and all I'm doing there is cutting off a corner. And look, I made a triangle just by cutting off a corner. So I made a triangle as a cross section. Okay, notice what else I could do. Had I cut this thing straight in half, so half there, and half there, notice that I could slice and put my knife straight through to create this shape. And most of you will notice that that shape is the same as this one over here, which is the same as this over here. Because all I've done is just slice straight through like a fruit ninja. And this ends up being what looks like a square. What other shape can we make? If we take our butter knife, we slice the corner off, we get a triangle. We slice straight down, we get this. Is there some other shape that you could make by making a different type of slice? Notice what one person did here. Just taking the kind of like cutting a ramp out. So going diagonally through, and notice what's formed here. Now, of course, it won't always look 90 degrees because of the nature of the three-dimensional shape. So in this case, it happens to look somewhat 90 degrees. But the ramp that's formed here, just the face part of that ramp, we see as a rectangle. Anything else? Did anyone see any more unusual shapes? So what if I cut in an odd fashion like this? What if I cut here, and I can cut straight down, so I cut the entire corner off like that, just down the edge of that. Notice I get this rectangle. But notice, what if I get a little crazier, and instead of cutting straight down, I cut diagonally down, but I start along the edge there. Can anyone take a gander at a guess at what shape this is going to be? It's going to be a trapezoid. How do I know it's a trapezoid? Because the top is going to be parallel to the bottom here. So we can cut a variety of different shapes, and each one of these is called a cross section. So how you take your slice of butter, how you take a ball and slice it, however you take a whatever and slice it, you get what's called a cross section. So please take a few moments here, and what is the cross section that gets formed? Now this one is kind of darkened for you, but these ones aren't darkened. So you might need to take a moment to darken the cross section to see what you come up with. So this one is probably a rectangle. This one is probably a circle. And this one is just unusual, hard to tell. So I'll just simply say a quadrilateral. All right, down here. Can you make a square by slicing this pyramid? And this is, by the way, a square pyramid, which means the bottom is a square. The base is a square in this case. Base does not always mean bottom, but in this case, the base and the bottom are the same. So since the bottom is a square, can I slice this somewhere and make a square? Can I slice and make an isosceles triangle? Can I slice and make a rectangle that's not a square? Can I make an equilateral triangle, a scalene triangle, a trapezoid? So go ahead and see what you can come up with. Some of these may or may not happen. So I gave a few of these down here for you to experiment with and see what you can find. Go.